right, good evening, you Bearcats. Just real quick note to you very creative Bearcats. It would be really fun to have another intro for my logarithmic section. Since you're also creative, I think we could have some logs to a rhythm. What do you think? Some get it? Logarithmic. I think that might be fun. Some logs and some rhythm. Anyway, all right, just a thought. Anyway, let's keep going. Go Bearcats. Today we're going to talk about logarithmic functions and their graphs. I'm just going to kind of read you some stuff out of the book. I actually cut and paste it so that you get used to reading your math textbook, which you don't do very often, but there's some really good information there. In section 1.9 we studied the concept of inverse functions, and we've already mentioned this this past week. But there you learned that if a function is 1-to-1, okay, if it's 1-to-1, and we talked about that recently, that is, if the function has the property that no horizontal line intersects the graph of the function more than once, that the function must have an inverse function. By looking back at the graphs of exponential functions, you will see that every function of the form f of x equals a to the x, that would be your exponential function, it passes the horizontal line test. Remember, an exponential function is either growth or decay, and if I drew a horizontal line and did a horizontal line test through those graphs, they would both pass the horizontal line test, and no matter which way we manipulate those, and they would pass the horizontal line test. Therefore, they must have an inverse. The inverse of this function is called a logarithmic function with base A. And we talked about that before. I said the more we know about exponential functions, the greater understanding we will have of logarithmic functions. Couple things that we should learn. We should learn to recognize and evaluate logarithmic functions with base A. We should graph them, and that's what we're going to do, those two things today. We're going to recognize, evaluate, and graph natural logarithmic functions. We'll talk about natural logarithmic functions tomorrow. That's the same thing except our base is e, just like it was our natural base e when our exponentials. And then we're going to use them to model and solve real-life problems. All right, let's go ahead and keep moving on. Definition of logarithmic functions with base A. And again, these are the blue boxes out of your book that are so important. Look here that x, in this example, y equals log base ax if and only if x is equal to a base a to the y power. Okay, remember they're inverses of each other, and we're going to take a look at that. I like to have my y on this side of my equation. I do this. I'll write log base ax equals y. And then in exponential form, what do? I keep the base, okay, I keep the base, and I switch out my x and my y. That's where my x and y switch. Remember, we've talked about that property with inverses before. So we have now base a to the y power is equal to x. And that's that inverse property that we've talked about before. A couple things that are important. Again, x has to be greater than 0. The same thing we talked about, our base a had to be greater than 0 before. A has to be greater than 0, and a cannot equal 1. A cannot equal 1. The function given by f of x equals log ax is read as follows. Log base a of x. And it's called a logarithmic function with base A. And we can have other bases. The bases can be different, just like our bases of our exponentials were different. So again, showing this whole change between our x and our y, here again, y equals log base ax. It can be rewritten in exponential form that x equals a base a to the y power. Again, like I said, I just prefer my y on the other side. It's just a personal thing. Either way is work. These are equivalent, and the first equation is in logarithmic form, and the second equation is exponential form. They are equal to one another. For example, and I like these two examples, and I'm going to change it up a little bit. I'm going to do it over here to the side. So if I have log base 9 equals 2, then remember, 3 is the base, so 3 becomes the base of the exponent, and these two switch. 3 squared equals 9, which is a true statement. We know that. In the exponential equation, 5 to the third power equals 125. Okay, so now we have exponential base 5 to the third power equals 125. Now all of a sudden the base will become the base of the log, so log base 5, and these x and y's will switch again. 125 equals 3. So we can go back and forth between bases, and you can go on and read. There's a couple of more here as well. And this is really, you know that 5 to the third power is 125, so that's how we know that to solve that. And there's another example that if you want to read about log base 2 8 here in this work as well. All right, we're going to keep moving though. All right, properties of logarithms. Properties of logarithms is kind of important, and we're going to use these in solving problems. So a little red note over here, and this was really to the teacher about students, but I think it was something I wanted to share with you, that logarithmic functions can be one of the most difficult concepts for students to understand. It is one that I do hear about from calculus students that is difficult for them, so the more we can learn about them now, the better that will be for you later. If you can remember that a logarithm is an exponent, okay, it's an exponent, and converting back and forth from the two forms can help support the concept and can help you understand logarithms better. So understanding that they're inverses is very helpful. All right, let's look through these properties. This is log base A1 is 0, and that is because A, and you switch to the 0 power, anything to the 0 power is 1. We have log base AA, that's because A to the first power would be A. We have log base A, x equals x, and that's, be careful, this whole thing right here is what gets switched with this. Be really careful about that. So you would have, I'm going to squeeze it in right here, you would have A to the x power equals A to the x power, which is true. And finally, log base AX equals log AY. And if that's true, then your x and your y would have to be equal, since the log base a's would be equal. That's a one-to-one property. As soon as our bases are the same, then we would solve the other. We had that in exponentials, where the base of the exponential was the same. It's like 2 to the 2x equals 2 to the 3, 2 to the third. Okay, the bases were the same. They were 1-to-1. Then all we solved was 2x equals 3. The same kind of principle. Remember, there's going to be a lot of similarities between the logarithms and our exponentials. All right, let's just do these three examples real quick. We're going to simplify. These are really not equal to anything. We're really simplify them. And to do that, I'm going to kind of switch forms. So I'm going to pretend like it equals something. So I'm going to say pretends like it's simplified to something. So I would have 4 to something equals 1. Well, anything to what power equals 1, that would be 0. So log base 4, 1 equals 0. Log base, any base 1 would equal 0. All right, for this one, again, we're going to pretend like it's equal to something. A lot of people use x. I'm a little leery about using x as my, what I'm imagining in my mind. I'm just going to use a question mark. So here I would have the square root of 7 to some power equals the square root of 7. Well, that would have to be 1. So anytime the base and the exponent in the base is the same, then it's going to be 1. And finally, we're going to simplify this. And remember, this whole log 6 base 620 is the exponent to that. So we would have 6, equals some question mark. We would have 6 to some question mark equals log 620. So that would also be 6 to the 20. And so this would have to be 20. If you have a base, and then the log of the base, the log of the same, you can kind of think of them as canceling out to get your answer. They become 1. They're 1-to-1, they become 1. That's the base of a log and the base of an exponent. And that would be left with your answer. All right, let's move on. All right, graphing. Graphing is going to be really important. Graphs are similar to our exponentials, except they're just inverses. And if you remember a lot from our inverses, inverses reflect over this y equals x line, which is important. To sketch, let's just read up here, to sketch the graph of y equals log base ax, you can use the fact that the graphs are inverses of and reflection over the y equals x line. Often, to graph logarithms, you will graph the parent function with the same base of an exponential. Listen to what I just said. So to graph a logarithm, you're going to graph its parent function of an exponential with the same base. then switch your x and y values. So I'm going to look at these two examples, and I'm actually going to start here and talk about in log form. This is log base 2. So to graph log base 2x, I would actually think about base 2 to the x power, which is what is over here. And I would do a chart or a table for that if I didn't know what that was. So we can even do that. So I'm going to pick -2, -1, 0, 1, and 2, which is often the values I pick. If I go 2 to the -2 power, that's 1 over 2 to the +2 power, or 1/4. This would be 1/2. Anything to the 0 power is 1. 2 to the first is 2, and 2 squared would be 4. And this would be our exponential function that we get right here after we graph those points. We would take these ordered pairs, and for the log, okay, for the log, here's our exponential. For the log, we're going to reverse our x and our y. So for the log base 2x, our table just switches. It becomes 1/4, 1/2, 1, 2, and 4 as my x values, and my y, or my output, is -2, -1, 0, 1, and 2. And that's what we get here. So notice what happens. At 1/4, we're at -2. So at 1/4, we're down here at -2. At 1/2, we're at -1. At 1, we're at 0. At 2, we're at 1. And at 4, we're at 2. And we end up with our inverse function, which is our logarithm function. Really important that you can think through the graphs based on exponentials, because exponentials you can calculate in your head. All right, and I think if you read, that'll tell you a little bit more about that. Let's move on. You'll be graphing some in your classwork tomorrow. All right, let's talk about shifting graphs of logarithms. Well, the nice thing about shifting graphs of logarithms is we're really talking about transformations again. And here's a study tip for you over here I think is really important. You can use your basic understanding of transformations to identify vertical asymptotes of the logarithm functions. And you'll see an example here. For example, in the graph f of x minus 1, f of x minus 1, then it shifts the graph 1 unit to the right. So the vertical asymptote would also shift to the right one. If it's x plus 1, you would shift to the left one. So you can use that principle for the asymptotes as well. Let's talk a little bit about asymptotes real quick. I'm going to go back and take a look at this. Notice that for an exponential, we had an asymptote here, a horizontal asymptote here at the x-axis. For our base logarithm function, we have a vertical asymptote. So in logarithms, if we shift left to right, our vertical asymptote would move. And for exponentials, if we shift up or down, our horizontal asymptote would move. And that makes sense. Remember, they're opposites. You flip-flopped your x and your y values. All right, let's go back to this page. So, again, basic transformations. Log x minus 1 would mean we would shift the graph to the right 1. And you already know that from your basic transformations. Let's look down here. 2 plus log x. Now, this is a little confusing because they put the vertical shift in the front of a logarithm. If you think about this, this would be the same as, and I'm going to go up and write it up here, if I had log x and then this positive 2 was at the end. We're used to often seeing our vertical shifts at the end of our function. In logarithms, they like to put them at the beginning, so be really careful. So that would basically shift our graph up 2 units, and it would look like this. So you're just going to use your basic concept from our transformations to sketch our graphs. You'll sketch a parent graph or a base graph and then just use transformations to move them around. And you'll get your base log graph by graphing your exponential graph and then taking your x and y's and switching them. So there's a lot of processing there and a lot you need to think about. All right. Finally, tomorrow's classwork, I went ahead and put it on here. You might want to write it down in your notes. It'll be page 229, 1 through 29, 21 odd, 27 through 30 all, 31 through 37 odd, and 39 through 44. Again, I think it would be really fun to have some logs jump into a rhythm for our logarithmic section. So you creative Bearcats, I think somebody should come up with some really cool idea. All right. Anyway, have a great night, and as always, Be safe and go Bearcats!